Hello and welcome to our presentation on the Comstock Bridge. Listed on the National Register of Historic Places, an official list by the National Park Service of historic places in the U.S. determined worthy of preservation, the Comstock Bridge is one of the 3 remaining covered bridges left in the state of Connecticut. It is located at the junction of Colchester and East Hampton, crossing the Salmon River.
This bridge was originally built in 1840. It used to be a road for travel, but major restorations were made in the 1930s after a truck crashed through the floor. It is now a pedestrian bridge and has gates at either side. The bridge consists of 2 parts, one 80-foot long covered howe truss bridge and a 30-foot span uncovered portion. The bridge has a width of 12 feet and the supporting beam is 1 foot thick. It's supported by a fixed end at one end with rollers in the middle and at the other end. We analyzed the bridge without the truss section and as one continuous beam in order to satisfy the indeterminacy requirement.
We used the software Autodesk Inventor to make a 3D rendered CAD model of our bridge. This software enables users to produce accurate 3D models to aid in designing, visualizing, and simulating products, and even has a feature to incorporate materials into the model.
In order to determine the dead load of this bridge, it was necessary to make the reasonable assumption that the material of the bridge is southern pine, one of the most common timber materials used for construction in the United States. We calculated the dead load of this bridge as a floor load calculation. Since there are beams running horizontally across the bridge every 2 feet, we could calculate it would be a distributed load on the beams. According to the AASHTO code, southern pine has a density of 37 pounds per square foot. With that, we could find the dead load by assuming the thickness of the supporting beams to be 1 foot each. We were able to conclude that the total dead load would be 222 pounds per foot. Originally, we tried to calculate this as multiple point loads, but we found that for our analysis calculation later on, it was much easier to simplify these point loads into one distributed load.
For the normal live load on a pedestrian bridge, the AASHTO code specifies a loading of 90 pounds per square foot. When selecting our load factor to account for the variability, we determined a medium to high degree of variability. Depending on the season or weather, the amount of foot traffic on the bridge could vary, so we decided on a load factor of 1.5. We multiplied this by our AASHTO specified live loading to conclude a total normal live distributed load of 135 pounds per square foot.
We used the force method to solve for the reactions at the pin and at the 2 roller supports. This method includes drawing influence lines and removing a support to make the structure determinate, and placing a virtual load at the point where the support used to be, and come up with compatibility equations that enable us to analyze an indeterminate beam as determinate.
The extreme loading condition chosen for analysis of this bridge is an ambulance. Because this is a pedestrian bridge, it is not designed to carry vehicle traffic, but it is reasonable to assume that in the case of an emergency, it may be necessary for the bridge to support an emergency vehicle. A standard Type 2 ambulance can be analyzed as a rolling load, with 2-point loads of 2.4 and 3.35 kips 15 feet apart. In practice, influence lines should be calculated for the moment at each support, and the ambulance load should be analyzed at the 3 different locations that cause maximum moment at each of the 3 supports. However, for the purposes of this analysis, we chose to analyze maximum loading conditions only for support C. Therefore, an influence line was drawn for support C and used to determine that the maximum moment due to the ambulance load occurs when the heaviest part of the ambulance is placed at support C. The reactions at each support were determined using the force method of analysis as outlined below and detailed in the attached hand calculations. The loading was also analyzed using STAD Pro. Results of both methods are summarized in the following table. The notable discrepancies between the hand-calculated and software-calculated reaction values can be attributed to a multitude of factors. While the hand calculation process is correct, it is likely that there was human error in the calculations at some point, and rounding error may have also been a factor. Additionally, lack of familiarity with the analysis software may have impacted the analysis results. The inputs seem correct, but there could be issues with the model that are not evident to an inexperienced user. Regardless, the difference in hand-calculated and software-analyzed results further emphasizes the value in analyzing a structure in more than one way. Overall, the project provided valuable insight into the structural analysis process performed by engineers working in the industry. The project incorporated several concepts from the course and served as an example of how these concepts can be used concurrently to solve larger-scale issues. The project also revealed the potential complexities of structural analysis, as many assumptions and simplifications were made to the real-world structure in order for it to be feasible for a basic level of analysis. Additionally, it was an excellent introduction to 3D drafting and analysis software, which are important skills to hold as engineers entering the workforce.